this video, we're going to start talking about limits, what they are, and how to tell from a table or a graph. All right, so here's just some, you can pause, write this down. This is just some vocabulary surrounding limits. So we're just going to say that we're given a function f of x for real numbers, a, so a is just a real number, and L is just a real number, okay? So this could just be anything. So the informal definition of what a limit is L is the limit of f of x as x approaches a. Remember, a is just any real number, okay? So any number that we could plug in as the input to a function, okay? So L is said to be the limit as long as the function approaches L as we are approaching a. So as we plug numbers that are getting closer and closer to a. So let's say, just to give you some context for that, because I know that that feels confusing. So if a was 4, so let's say a was 4. So as we plug numbers in that get closer and closer to 4, like 3.9, 3.99, 3.999, as we get closer and closer to 4, or from the other direction, 4.1, 4.01, 4.001, as we're plugging numbers into the function, okay, that are getting closer and closer to 4, that the output gets closer and closer to L. Okay, so that all of those numbers just get closer to L. So let's say that L was 3. So as we plug in numbers closer to 4, this gets closer to 3. Like maybe it's spitting out 2.5 and then 2.7 and then 2.9, 2.99. Just gets closer and closer to that. Okay, so as x gets closer from both sides, the corresponding of values of f of x, or the output, get closer and closer to L. That's what I just talked about. Okay. And the value of f of x can be made as close to L as desired, okay, by taking numbers closer and closer to a. So if I want to get even closer, so if I wanted to get to 2.99999, that's fine. We just would have to find a number closest or very close to 4 to plug in, but that just exists. So what does that actually mean for you trying to do some limits, okay? So let's take a look at a graph here. Okay, so we've got this quadratic, we've got this parabola. So we want to look at the limit as x approaches 2. That's how you read that. The limit as x approaches 2 of this function. So let me just highlight where 2 is at on this graph. Okay, where x equals 2 is at. So remember, this is the line x equals 2. So what we're talking about is as we plug in numbers on this graph that are getting closer to 2 from the left, okay, so meaning numbers smaller than 2, okay, and you'll see that on this side of the graph here. Okay, so we have these ones that are getting closer and closer to 2 from the left. And then also numbers that are getting closer and closer to 2 from the right, meaning numbers that are bigger than 2, okay, on our way towards 2. So, I mean, you could start at 7, 6, 5, 4, 3, 2.5, 2.4, 2.3, 2.1, okay, but just, we generally do a 10th below and a 10th above, and then just start getting closer, okay? So this one is just a 10th above, this one's a 100th above, this one's a 1,000th above, so just getting closer. This one's a 10th below, 1/100th below, 1/1000th below. Then we would plug these in to this function, okay? So now we're plugging in 1.9, so you'd be, so you'd be doing 1.9 squared plus 3 in your calculator, and you'd be doing 1.99 squared plus 3. And you'd be doing 1.999 squared plus 3 and seeing what those outputs are. So when we plug 1.9 in, we get 6.61. When we plug 1.99 in, we get 6.96. When we plug 1.999 in, we get 6.996. So what are these numbers getting closer to? So we're at 6.6, 6.96, 6.996. These are getting closer to 7. So then we'll check on this other side too. Okay, so a 10th above 2 gives us 7.4. A 1/100th above 2 gets us 7.04. And then 1/1000th above gets us 7.004. So these numbers are getting closer to 7, and so are these. And if we take a look at following that on the graph, okay, so as you start plugging in numbers that are getting really close to this line, okay, your output is getting closer and closer to 7 on that side. And as you plug here, okay, the slope of this line is coming down, so those numbers are getting closer and closer to 7, started above, getting closer and closer to 7 again. Okay, so they're both approaching this y value of 7. So that's said to be the limit. Now we can actually also go ahead and plug 2 into here, okay, and we're getting 2 squared plus 3, so 2 squared is 4 plus 3 is 7. Now this does not have to happen. These don't have to match. So just because f of 2 is 7 doesn't mean that the limit is 7. Okay, in this case it was. We've got a continuous function here. So let's take a look at another table. So this one has a line with a hole. Okay, and what that hole means is that we had a factor cancel out here, okay, which we'll get into later. But if we factored this top piece, and it has an x plus 2 factor in it. Let me just do that. So factors of 8 that add to 6 are 4 and 2. So this top piece factors to x plus 4, x plus 2, and we have that x plus 2 on bottom. So what actually ends up happening here is those cancel. That creates this hole at x equals -2, which is the bad domain value because you would get division by 0. So in this problem, if we plug -2 in here, which is the limit in question, the limit as x approaches -2 of g of x, so this should say g of -2. Okay, so let's figure out g of -2. Well, if you plug it in, okay, and you do -2 squared plus 6 times -2 plus 8, okay, on top, and then -2 plus 2 on the bottom, that bottom is 0. So anything divided by 0 is undefined. So you actually can't plug -2 directly into this function. Now, when we look at the limit, though, the limit has nothing to do with whether the function is defined or not. Okay, the limit is what is the function doing around this value, right below it and right above it. So again, we're going to plug in numbers that are just below -2 to be checking out this left side. So as we come at -2 from the left, what is happening? Okay, and here's -2. Okay, so as we come at -2 from the left, so numbers just below -2, what's happening to our function? Okay, and then as we come at -2 from the right, what is happening? Okay, so plugging in numbers just below -2 and just above -2. So plugging in -2.1 into this function gives us 1.9. Plugging in -2.01 gives us 1.99. -2.001 gives us -1.99. Okay, then plugging numbers in from the right, so just above -2, so a tenth above -2 is -1.9, gives us 2.1. -1.99 gives us 2.0. -1.999 gives us 2.001. So from the left, these numbers are getting closer to 2. From the right, these numbers are getting closer to 2. So the limit of the function, so like right around this -2, the function is getting closer and closer to an output of 2. And you can see that in the slope of the line. So if you take a look here, as you get closer and closer from the left, you get closer and closer to this value. As you get closer and closer from the right, you get closer and closer to this y value, which is 2, like we found in the table. So I've been talking about from the left and from the right, okay? And so as long as those two are the same, so they're going to 2 on the left and they're going to 2 on the right, that's said to be the limit, okay? But coming up at it from the left, numbers below the x value in question and then coming from the right, numbers above it, those are said to be one-sided limits, okay? And the limit, the overall limit, exists only if both of the one-sided limits, the left limit and the right limit, are identical. Okay, so when we just see this, the limit as x approaches a of f of x, that limit exists, like it did in the last two examples, if approaching the number from the left and approaching the number from the right is the same. Okay, so let's just say here's your A value. When you're plugging this in, if the numbers that are coming in from the left and the numbers from the right are the same, then this limit exists, okay? So left hand, the notation for that, you're gonna see this little minus sign. So this one is the limit as x approaches a from the left of the function is L. And if the limit as x approaches a from the right, this plus sign of f of x is L, then the overall limit exists. If this number and this number are different, then the limit does not exist. Okay, left-hand limit exists, right-hand limit exists, but the overall limit would not exist if these two outputs are different. Okay, so notice A with an exponent of a minus sign means from the left, and A with an exponent of a plus sign means from the right. So then let's take a look at these graphs. Okay, so on a graph, the limit A exists if as you approach A from both sides, you're also approaching the same height. So we kind of looked at it on these other two, okay, but it's almost as if you could put your finger on the graph and follow it to a specific line. So both fingers, one on each side, and see if the graph is approaching the same value from both the left and the right. So let's take a look at what I mean by this. So if we're looking at, let's say, the limit as x approaches 6, okay? So here's the x value in question. And so when we look at this line, so follow your graph. If you started way over here, like your graph, you'd keep following it. Okay, it doesn't really matter what it's doing over here. Okay, it matters what it does when it gets really close to this line. Okay, what's the height? That's from the left, and then from the right, what's it doing from the right? And you see how from the right and the left, it's pointing at this same height of around negative 3.2. That means the limit exists, and it is whatever that height is. Okay, so let's take a look. So if we go over here and we do the limit as x approaches negative 2 from the left. Okay, so where is the graph going from the left? Okay, so following it, starting low and going high, getting closer and closer to that number, right? So when you're following this with your finger, it's as if you're plugging in negative 10, negative 9, negative 8, getting closer and closer, negative 4, negative 3, negative 2.5, negative 2.1, okay, and getting closer. So this one, as we approach from the left, is going towards a height of 1. And then when we come at it from the right, okay, so coming high x values and getting closer and closer to negative 2, it goes to a height of 1 as well. So the limit, if I were going to write this out, the limit as x approaches negative 2 of this function equals 1. And that's because the limit as x approaches negative 2 from the left of f of x was 1. That's that blue side. And the limit as x approaches negative 2 from the right of the function was 1. And since both of those limits from either side were equal, then the overall limit exists. So a place where the overall limit wouldn't exist would be something like this. Because in this one, as you're approaching from the left, okay, so coming at this function from the left, we approach 5. Okay, so the height here is at 5. And as we approach from the right, this one is going towards negative 7. So the limit as x approaches 2 from the left is negative 5. And the limit as x approached 2 from the right was negative 7. So the overall limit as x approaches 2 does not exist. And I'm just going to write DNE as shorthand for that. So it does not exist because those were different. So there's 3 cases also that limits don't exist. Okay, the first one is what we just talked about where they approach different heights. So this x value right here, okay, x equals 2, this limit does not exist. Everywhere else it does because we've got continuous functions with no breaks. This is the one spot on this graph that it doesn't exist because from the left and from the right are approaching different values. Okay, so from the left, we're approaching this height, and from the right, we're approaching this height. Okay, so approaching 2 versus approaching -1. That's one way. Another thing where the limit doesn't exist because, so when it's going towards infinity, because infinity by definition isn't a limit, it's unlimited, so it just continues to get larger and larger and larger. Okay, so that's not a limit. It's not getting closer and closer to 2 or closer and closer to 4. It just continues to get large. Okay, so now if on both sides, so this red line is where we're approaching the limit of -1. From the left, it's approaching infinity. From the right, it's approaching infinity. So we would still say that the limit as x approaches -1 of the function is infinity. Okay, both sides are going towards infinity. So it does tell your reader something about your function. Okay, so we don't necessarily write that it does not exist. We would say that it's going towards infinity. One way that it would look if you were saying that if we were going to say that it doesn't exist overall, something we couldn't tell the reader is if we're looking at this line here and we see that the graph on the left is going towards infinity and then the graph on the right is going towards -infinity. So this one we wouldn't be able to tell the reader the overall limit because one side goes to infinity, one goes to -infinity. So the left-hand limit here would be infinity, the right-hand limit would be -infinity. Then there's this one that says that if you have a function that oscillates infinitely many times, so it's just going back and forth as you get closer and closer to the number in question. Okay, so it's just sitting there oscillating back and forth, which means going up and down, up and down, up and down at that number, then we would say that one doesn't exist. All right, so let's take a look at this graph, and it's just going to ask you some different questions about this. So f of -4 means plug -4 in, so go find -4 on your graph, plug it in. Okay, so remember it's defined at this point, so it's not defined here. Okay, so this graph at -4 is 0. The output is 0. Now the limit as x approaches -4 from the left. Okay, so I'm just going to cover this up and say we're going to approach -4. So let's take a look at the graph, and as we're getting closer and closer to -4, okay, where's this graph going? So follow along on this graph. Okay, where is this graph going as we get closer and closer to -4? Not when we hit -4. Okay, so it's as if you almost can't see -4, but where is this graph going towards? So it's going towards this height right here of -1. Okay, so if we couldn't even see what the function is actually doing at -4, what is it doing right next to -4? And it's going to 1. So the left-hand limit here, or sorry, -1. Okay, so as we approach it and we just get really close, it's going to -1. Then the right-hand limit as we approach -4, so as we come at it from the right, so if we could just kind of move the screen back and keep going until we get to -4, get very close to -4. So following this function, so your eyes are here, following this function as we get closer and closer to -4. So what is that function doing as we get closer and closer to -4? And it's again going to this height of -1. And then when these two are the same, when the left hand and the right hand limit are the same, that means the overall limit is also -1. Okay, if they're pointing at the same value here from both the left and the right. So if you were following with your finger and you went towards this one and following with your finger here, you're going towards this height on both sides. That's your limit of -1. So again, doesn't matter about whether it's defined there or if the function at -4, what that is. Okay, just what's the function doing around those values. plugging in -2 to the, or sorry, +2 to this function. So here's +2. So what's the function at +2? So the actual defined function, okay, the actual value of this function at 2 is -7. Then this one says as x approaches 2 from the right. Okay, so the right-hand limit, so coming at it from the right side, this function from the right side is going towards -7. The limit as x approaches 2 from the left. Okay, so from the left, coming at it from the left, where's this going towards? Okay, and it's going towards -5. So then you look at the left-hand limit and the right-hand limit. So left hand is -7, right hand is -5. So this overall limit does not exist. And on the graph, again, you can see that because there's a break. Okay, so there's a break at this x value of -2, and there's this jump. So this side is kind of ending at -5 of a height. So the left side is ending at -5 as a height, and the right side is ending at -7 as the height. So then the overall limit does not exist since they're going to different heights. So let's take a look at a piecewise function and how do we tell a piecewise limit, okay? So I have the graph here, but let's use this for when we don't have a graph, and then we'll look at it on the graph. Okay, so remember that when you're plugging in and trying to figure out the actual value, so what is f of 3? We look to where we would plug this in. The equals to 3 is on this bottom, so we would plug it into this function. So we would be doing -3 plus 4, which is 1. Okay, so just plugging it in. Now, if we were going to be doing the limit of f of x as x approaches 3 from the negative side, remember this is smaller than 3. Okay, from the left means smaller than 3. So we're going to be looking for the part up here where x's are smaller than 3. So this is x is less than 3, so we're going to be plugging into this one for the left-hand limit. This represents this left side of the graph. Okay, so this final value is going to be what the limit is when we get here. So we'll take the 3 and we'll plug it in to this one. So we'd have 3 squared minus 3 times 3 minus 2. So we'd have 9 minus 9 minus 2. So -2 would be the limit from that side. Then when we want to do the limit from the right side, so this means numbers that are bigger than 3. So then when we're looking at the domain up here, we want the one where the x's are bigger than 3. That will represent the right-hand side of the graph. Okay, so x is bigger than 3 will plug into here. Okay, so then we'll do -3 plus 4, which is 1. And again, when you look at it here, okay, that's matching that right-hand side is going towards a height of 1 versus the left-hand side was going towards a height of -2. So then the overall limit, when we look at the left-hand limit and the right-hand limit, they are different. So this overall limit does not exist. Then let's look at the limit as x approaches 2 here. Okay, so then 2 is less than 3, so we can plug it into this top part. So we do 2 squared and then -3 times 2 minus 2. So we get 4 minus 6 minus 2. And so 4 minus 6 is -2 minus 2 is -4. And we could look here. Okay, so here's x equals 2. So from the left, it's here, and from the right, it's here. That's at a height of -4, so that matches on our graph to what we just did there. And then final one, plugging in 5. So 5 is greater than 3, so we can do -5 plus 4, which is -1. Taking a look at this graph again, so 1, 2, 3, 4, 5. Here's that value. we see from the left, it's going towards -1, and from the right, it's going towards -1. So the overall limit would be -1. So the only kind of places that are in question in these piecewise functions is the boundaries, okay? Because if the boundaries are going to different heights, then your limits are going to be different. So then otherwise you can just straight plug them in, and then you can also compare to that graph.